Hello everyone, here we'll be discussing hypothesis testing, and I kind of just want to cut to the chase and discuss the main goal for this video and certain hypotheses, which is of course plural for hypothesis, in our testing, and then the process of the actual hypothesis testing. Right, so I'm going to try to explain. There are a lot of details here, so just kind of keep that in mind. Now, the main goal is to test a certain claim with a given confidence or significance. Now, recall from our conversation on confidence intervals that confidence is CL, and then significance is alpha, and of course CL is 1 minus alpha. It's just the complement of the significance, basically. So, for example, if confidence is 0.95 or 95%, then alpha will be 0.05, which is a pretty common level of significance, actually. Now, as far as hypotheses go, there's what's called the null hypothesis and the alternative hypothesis. And depending what book you're using, it may be explained a little differently than how I'm about to explain it. So I'll explain it here and then I'll kind of try to elaborate. So here I say H naught or H sub 0. The null hypothesis is a statement that a certain parameter has a given value. Whereas the alternative hypothesis, H1, is the statement that the parameter from H naught, from the null hypothesis, does not have that given value. In other words, it could be not equal to, bigger than, or less than that value. Now, this is described as a two-tailed test. This is described as a right-tailed test because we're bigger than this value. And less than, of course, is described as a left-tailed test. Now, I mentioned earlier that depending on the book you're using, the explanation may be a little different. Basically, the null hypothesis is sometimes referred to as the complement of the alternative hypothesis. Now, what I'm going to be describing is not that. So generally, what I'll be showing you is that H naught will be something like, for example, mu is equal to a number, and H1 will be something like that mean mu is not equal to that number. This would be a two-tailed test. But notice equal to and not equal to in this case are actually complement. So one says something, the other one says the opposite of that. They're kind of complementary statements, if you will. But if our alternative hypothesis was bigger than, then technically the null hypothesis then will be less than or equal to, and not just equal to. So that's that kind of other explanation depending on the book you're using. But I'm not going to be discussing that. So for our cases, for our purposes in this video, I will be assuming that the null hypothesis is that the parameter has that exact given value. Now, something that we'll be describing soon will actually basically tell us that the null hypothesis is assumed to be true. So we're essentially always assuming the null hypothesis to be true, and we're going to prove, given our statistics techniques that we kind of saw from confidence intervals basically, that the alternative hypothesis may or may not be true. Now, the wording is a little specific. So instead of saying that given our significance level or confidence level, the alternate hypothesis is true or accepted, we'll instead say either we reject the null hypothesis, or we do not reject. Now, to reject means that you, not that you don't accept. Again, the wording's a little funny, but reject it just basically means that we're denying that to be true based on our statistical evidence. That's all we're saying. Doesn't mean it actually isn't true. It's just based on our statistics, we would have to reject it or not reject it, depending. So I hope that part kind of makes sense, and we'll have to see that more with an example or two. But let me try to describe the process here. And the first step of the process is to state the hypotheses, H naught and H1. So null and alternative hypothesis. 2 would be to calculate the test statistic. That'll actually be our, essentially our key to unlocking whether we can reject or not reject the null hypothesis. More on that in the next screen. And 3 is then to determine what is called a p-value, and this depends on H1. So your p-value could be a result of a two-tail, right-tail, or a left-tail test. And again, we'll discuss more on that a little later. And step 4 would then be to decide whether or not we reject the null hypothesis or not. So for right now, let me just say the following. There's kind of these two scenarios for p-value anyways. So either the p-value is less than the level of significance or bigger than the level of significance. I guess it could possibly be equal to. If it's a close call, we'll just say that's bigger than. Right. But your p-value will never exactly be equal to alpha, but if it is equal to alpha, we'll just assume that that is this case. So if it's less than alpha, then we will reject the null hypothesis. And if it is not, then we do not. Now again, the significance of this, as far as what this means in terms of what we're actually deciding, what our decision really means, is that to reject the null hypothesis says that there is enough statistical evidence to support the claim of the alternative hypothesis. Now the actual claim could vary. Usually your claim will be the alternative hypothesis. And in this video that will certainly be the case. But again, depending on the book, there are certain scenarios where your claim is actually the null hypothesis. And it just depends on the wording of the question as well. But again, we'll take a look at a few examples and see. So rejecting the null basically implies that there is sufficient evidence, I'm going to use some shorthand here, to support the alternative hypothesis H1. Whereas if we do not reject, it kind of cut off there, so let me move the screen, or move the camera a little bit. There we go. And if we do not reject the null hypothesis, then there is insufficient evidence to support H1. So I'll just write insufficient evidence just because, of course, I don't have too much space here. Good. So now, now we're going to take a look at specifically what this means, because this is still a little uncertain, and specifically what this means. Now, I've kind of explained, what P does for us. If P is less than alpha, we reject. If P is bigger than alpha, we do not reject. So that makes sense, I think. At least this part of it should make sense. But what P actually is, how we find P, I haven't shown you that. What the test statistic actually is, and that depends on the parameter. Now, the parameter, as we kind of showed here, was mu, but it could actually be mu, it could be sigma, it could be the population proportion, P, it could just be really anything to do with the population. So it's a population parameter. All right, so one thing I want to say before we move on again is just that a lot of what we'll be discussing here has a lot to do with what we saw with confidence intervals. So we'll kind of see that when we write the test statistic, you'll kind of be reminded a little bit of what we saw with confidence intervals. And there's a lot of parallels between the two. But here we'll kind of be using it. In fact, one can say that hypothesis testing is really an application of confidence intervals to, reject a claim or not. Anyways, we'll move on to some examples after I explain these. So let's take a look at this explanation right now, and then we'll see some examples. Right, so the test statistic for mu, when sigma is known, is z naught, or z sub 0, equals x bar minus mu naught over sigma divided by radical n. So we know what these values are. We know sigma is the population standard deviation. We know n is the sample size. We know x bar is the sample mean. And mu is kind of, the given value from h naught. So when you have h naught is mu equals to mu naught, that is our guy right there. That's what the mean is. So it's basically what we're assuming the population mean to be from the null hypothesis. Because again, the null hypothesis is what we kind of assume to be true, and the alternative hypothesis is yet to be seen depending on our evidence, basically. And P is given by this. It's either normal CDF from z naught to infinity, or from negative infinity to z naught, or 2 times that of absolute value of z naught to infinity. Let me try to explain. So basically what happens is on the z curve, we have this normal curve, and z naught is either here or possibly over here, depending on your test. Now, if it's a left tail test, for instance, and z naught should be negative, so it's going to be on the left of 0, basically. And with that being said, the tail region is what we want to find. So P is basically going to be our tail end region, so our area. So if it's over here, for instance, then we definitely want to go from negative infinity to z naught, hence why that's the case here. But for a two-tailed test, we actually need both of them. So what we could do is we can actually take both of these areas in that case. So that'd be going from negative infinity to z naught, and then from z naught to infinity, and adding those results. But, as you might imagine, since this area and this area are the same by symmetry, if this is negative z naught, for instance, then the absolute value of z naught will just be this positive one, and then taking that area and multiplying it by 2 will account for both of them in the two-tailed case. So I hope that part kind of makes sense. We'll again have to see a few examples to kind of see really what's going on. But let's take a look at this quick example where I don't even give you any context, I just give you the values. So we have these given null and alternative hypotheses that mu is equal to 70 and mu is less than 70. And then we're given some values here from basically our statistics or from our sample, and again sigma is known here, and we're given our level of significance alpha. Good. So the fact that this is less than, it tells me that this is certainly a left tail test. So that means we got to use this one. Good. But first, before we even consider that, we of course need to find the test statistic z naught. So let's do that. So z naught is x bar minus mu naught, which is this guy here, so mu naught 70 for sure, divided by sigma over radical n. So now notice this is going to be negative 2, and this is going to be some fraction, and we have to divide. So I'll use my calculator off screen to evaluate this and approximate it, of course. But notice it is definitely going to be a negative value. Like I said, should be the case for a left tail test. So let me see what my calculator gives me for this now. All right, so my calculator gave me about 4.95, or I'm sorry, 4.59 is what I meant to say. There we go. Now, I must say that if you're using your calculator and you get something different, well, this actually is the correct answer. The reason why you may be getting something different is the way you type it in your calculator. So make sure that this numerator is handled separately and this denominator is handled separately. So the best way of going about that is, of course, writing parentheses in these specific locations on your calculator when you type this out. Otherwise, you have to do them separately and then divide those results. So that should guarantee that we get the correct calculation, and you should get something like this. Good. So now that that's the case, we've recognized, of course, it is a negative value, and we want to find the tail end. P represents the tail end. Since the left tail, we'll look at the left tail. So in this case, our z naught value is going to be somewhere over here, and it's negative 4.59. And the area we want to find is what we call P. So P is this left shaded tail end region. Perfect. So now to find P of course will be normal CDF, area under the normal curve, from negative infinity to negative 4.95. I kept saying 4.59, sorry about that. Now, of course, in your calculator, notice that negative infinity isn't really an option. So just type in a really large negative number, like negative 999 works, or negative 10 to the 99 is the largest negative value the calculator can interpret, at least for my calculator anyways. And I actually did this already, and I got a crazy number. I got 2.189 something 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 e negative 6. Now, just seeing that 2.19, that already is kind of throws some alarms off my head. And the reason why is because the p-value is an area, and we know area under the curve will always be a decimal less than 1. But 2 point something is bigger than 1, so that can't be the case. But this e to the negative 6 part, e negative 6 part, saves the day because that means it's really scientific notation, times 10 to the negative 6. So in reality, this actual value is 0.0000050 2189. Because if you grab the decimal and move it to the left 6 places, you get this. And this for sure is definitely less than our level of significance, 0.05, which is fantastic. Because remember, when p is less than alpha, then you reject the null hypothesis. So from here we can say we reject the null hypothesis, in which case that means that there is sufficient evidence to support H1. So let me just write that out. Now the way I'm writing it, you may think, well, which one's the answer? They're both kind of the same, actually. Now, in general, what we want to do is just write out a complete sentence, which is basically saying at the alpha equals 0.05 level of significance, there is enough evidence, there is sufficient evidence to support the claim of H1. Now, depending what the claim actually is, then we can actually write it out, which we'll see in an actual example now. So this is just a quick example using values to actually showcase the formulation I've written here. So now let's take a look at an example, and then we'll look at another scenario where sigma is unknown. Right, so in this example, we're given a report from 1996 that states that the mean number of pairs of shoes owned by someone in the United States is 6. A national survey, recent national survey, asks 150 Americans how many pairs of shoes they own, and the mean from this survey is 6.25, which notice is larger than the previous mean. Okay, now I want to test the claim that the national average has increased since 1996. Now notice that from the survey, assuming again that these are random people that are being asked, quite a large number of them, but it's only a little bit more than this. So we'll have to see how that weighs out with our level of significance. And again, we want to test this claim at the alpha equals 0.05 level of significance, and we're assuming that the population standard deviation sigma is 1.27. Now, we have all of the key ingredients to answer this question, and it won't take too long actually. The first thing we need to do though is we need to find out what H0 and H1 are. And this was the first step of the process I explained at the very beginning of this video. Now H0, again, we're testing the mean, population mean, and that's all we're basically going to be testing in this video anyways. But again, it could be sigma, or it could be the variance, sigma squared for instance, or it even could be a population proportion P. But in this case, it's the mean. So the null hypothesis is that the mean is what it was from the previous report, so that's 6. And here we're asking if it increased. So this is actually a right tail test. So that makes sense because we're claiming that the mean is national average, the population mean is now bigger than 6. So this is our claim, but more importantly, it's a right tail test. Perfect. So that'll tell us how to find P, but regardless of how we find P, Z0 is the same no matter what. So let's find our test statistic, Z0. So that again is the second step of the process, is to find the test statistic, which is Z0, and it is going to be, well, X bar minus mu naught over sigma over radical n. So now what is X bar? X bar is a sample mean. The mean of the survey is just the sample, is 150, so that's going to be X bar. I'm sorry, the mean is 6.25, that's going to be X bar, there we go. What's 150 though? 150 is the amount of people that were being asked this question, so that's the sample size n, there we go. And what else do we know? Well, we know sigma, that's just straight up given to us, sigma equals this. And our level of significance is then alpha equals 0.05. Notice the number 1996 is kind of irrelevant to the evaluations. That's just in the context of the question itself. So now if we plug these values in, we get 6.25 minus 6, all divided by 1.27 over radical 150. So I'll just be using my calculator off screen to evaluate this, and then after I evaluate this number, then step 3 is going to be asking us to find P. And remember, for P, it's going to be either left tail, right tail, or two tail. It's right tail in this case. And we know to finding the right tail of Z0, the right tail end area of Z0, well, that's going to have to be from Z0 to infinity for normal CDF because it's a Z curve. So this is going to be normal CDF of this value we got from step 2 to infinity, and we'll see what we get here. And then after we get this value, we want to see if that is bigger than or equal to alpha. I'm kind of getting ahead of myself, but let's find this first, then we'll plug it into normal CDF and see what we get. Right, so for our test statistic in step 2, my calculator gave me about 2.41 if you round to 2 decimal places. And I kind of did the next step here. If we take normal CDF from 2.41, this previous value, our test statistic, to infinity, we get about 0.008. And that is extremely good. That makes me very happy, because it's less than our level of significance, which is 0.05. So because of this, from step 4, or for step 4, since our p-value is less than alpha, so again, what this really says with the values is 0.08008 is less than 0.05, so that implies that we reject the null hypothesis. So it's kind of funny because rejecting sounds like a bad thing, but that's kind of the case you want to be in. Otherwise, we do not reject the hypothesis, in which case we can't actually say things have changed, kind of saying that maybe our survey was useless. Of course, it's not useless. It tells us something. It tells us that it's not a significant change. Now, it doesn't look like a significant change, but with this amount of people and with this other value given and assumed to be true, then it seems to be significant enough actually, because, well, according to our calculations here, we need to reject the null hypothesis. And again, that implies that we support the claim that it has increased. So now I'm going to erase this and write our actual statement that's the conclusion to this problem. All right, so from what we just found out, p is about 0.008, which is less than alpha, which is 0.05. This tells us that we reject the null hypothesis, so that there is sufficient evidence at the alpha equals 0.05 level of significance, just write it like that the national average of number of shoes owned in the US, number of pairs of shoes owned by someone in the US, has increased since 1996. Awesome. So this, in reality, is our grand conclusion. In other words, the answer to the problem. Now again, maybe rejecting the null suffices because that just implies this, but again, it just kind of depends. Now, in general, yeah, I would like you to write this statement because it tells us really the purpose of what we're doing here. We can actually say yes or no, which is kind of funny if you think about it, because you may think, well, we're doing all this work just to answer a yes or no question. But the whole purpose is that it's if it's a significant yes or a significant no. Now, with that being said, it doesn't necessarily mean that it is indeed the case. It just means that the statistics imply that that's the case. In fact, it may be true that it's not the case, but we just, maybe our sample's wrong, or maybe the sample doesn't tell us exactly what's going on, just depending how random the sample is, or maybe it's not large enough. There are certain things that may lead to that. And these scenarios are known as errors, of course. And there's what is called a type 1 error and a type 2 error. Basically, you were right when you were wrong, or you're wrong when you're actually right. In other words, it could be the case that this is incorrect, but we rejected and we shouldn't have rejected. Not that we shouldn't have rejected, but just that we're rejecting because the statistics implies that, but it actually isn't the case in general. So it could be the case that, let's say, the mean is actually known, but that's difficult because you'd have to ask every person in the US if, how many numbers of pairs of shoes they own in this case. And if it's something that is actually less than this, then we're wrong. And that's, I think, a type 1 error. And the other way around, if you do not reject the null, but it's the case where it actually does support the alternative hypothesis, that's known as a type 2 error, I believe. But again, we don't really have to worry about the types of errors. That's just something that comes to mind. So now, we've seen this example. I think it's a pretty good example. And now what we're going to do is we're going to talk about the scenario where sigma is not known, and kind of like you probably suspect, this involves the t-distribution, the student's t-distribution that we saw back in confidence intervals. So let me erase this and we'll talk about the test statistic for that and move on from there. All right, so just like we guessed and kind of said earlier, the test statistic for mu when sigma is unknown involves t. So our test statistic in this case is called t sub 0 or t naught, which is kind of the same thing we saw for z naught, only with s instead of sigma. So it's x bar minus mu naught, which again, mu naught is a given parameter from the null hypothesis, and divided by s over radical n. So basically the same thing, only with s instead of sigma. And p is very much the same thing, only slightly different. So instead of normal CDF, now we'll be using TCDF, because this is under the normal t curve, or not normal curve, but the student's t curve now. And of course we need our degrees of freedom, which we know from before is just n minus 1. Our sample size is minus 1. And for the right tail test, it's going to be TCDF from t naught to infinity, which would be this right tail here, and comma your degrees of freedom, n minus 1. And for the left tail test, it's going to be from negative infinity to our test statistic. So depending on where our test statistic is, either if it's a right tail or left tail. Of course, if it's right tail, it's going to be on the right, and if it's a left tail, it's going to be on the left. So positive versus negative, because again, for the normal, I keep saying normal, but for the standard t curve, our mean is 0 and our standard deviation is 1. Now for two-tail, we need both of them. So depending if your test statistic is either negative or positive, you just basically find that corresponding tail end region and double it. But here, to be generic, I write the absolute value of that to infinity, comma degrees of freedom, and then multiply that by 2 will result in both of those. Good. So now for this example, we're given, again, this is kind of like the quick example like we saw previously where sigma was known. We're given our null hypothesis, our alternative hypothesis, x bar, s, n, and our level of significance, alpha, which is 0.01 in this case. Now, here our null hypothesis says that the mean is 5.2. Here our alternative hypothesis says that it's not equal to 5.2, which is a two-tail test, which we haven't seen yet. Good. All right, so now what? Well, I guess we have to find t naught. So t naught is going to be x bar, which is 4.9, minus mu naught, this is our mu naught here, 5.2, all over our standard deviation, sample standard deviation 1.23, divided by the square root of 13. Now I already did this on my calculator off screen, and I got about negative 0.88 if you round. It's a pretty small negative number, it's not that large. So this is doubtfully true. In other words, I don't think we're going to actually reject the null hypothesis in this case, but we'll have to see. Basically, I think it's too close to 0 for the tail end region to be less than 0.01. And even worse, it's two tails, so we have to double that even. But let's see. So now that we have this critical value, not critical value, but this test statistic, I meant to say, we can find p by considering, again, it's two-tail, so it's going to be 2 times TCDF from this positive value, because absolute value of this, so that's going to be 0.08 now, or 0.88, there we go, to infinity, comma, degrees of freedom are 12 in this case. Good. And now, taking this and multiplying it by 2, I did this already, and my calculator gave me about 0.396, which is about 0.37 if you round, I guess. Which is not good, because this is definitely bigger than alpha. So, in other words, it is not less than 0.01, which is alpha. So that's bad. That means we do not reject the null hypothesis, which we haven't seen before, but now we kind of see how that works. It's when we don't get what you expect to get. So we do not reject the null, meaning that there is not sufficient evidence or insufficient evidence to support the alternative hypothesis. So that implies insufficient evidence. Everybody's a sad face. To support the alternative hypothesis H1. And now we're going to see an actual full-blown example, if you will, where we'll have the sentence, we'll have to determine what these values are based on the sentence, and then hopefully we can come up with a conclusion, kind of like we did with the previous problem. So let's take a look at that example right now. Right, so now this next problem has to do with speed solvers and Rubik's Cubes. So when making this problem, I was going to make an actual believable time. 25 seconds is kind of slow. So I wouldn't really consider myself a speed solver, but this is what I claim to be my average time. And I solved the cube. I really like Rubik's Cubes, by the way. So I solved the Rubik's Cube 5 times off screen, and now I'm going to attempt to solve it the 6th time here live. Well, kind of quote unquote live for you. So believe me, this is scrambled. I'll solve this right now, and then afterwards we'll test the claim at a confidence level 95% that my actual average is lower than 25 seconds. So let me just look at this real quick, which is allowed, by the way. And let's take a look. I'm going to set my timer, and here we go. Okay. Gotta be quick. So far it's looking not too bad. 11 seconds, something like that. Okay. I think this, yeah, there we go. Okay. Whew. Nice. So that was about 21.7, we'll round it up to 21.8 seconds. Whew, not bad. And notice one of the times is actually more than 25 seconds, so it's not obvious what's going to happen here. Now, what I'm going to do is I'm actually going to use one var stats in my calculator, and I have all these inputted except for the last one. So the last one was 21.8, and now one var stats gives me that the average from this mean is, let me actually write that over here. So from one var stats in my calculator, we get that the mean of the sample x bar is 24.45, so let's just say 24.5, and the standard deviation of the sample is then 3.27. All right. So let's go ahead and test the claim now. Now we need our t test statistic, but more than that, before we begin, our first step here, remember, is to find the hypotheses. Now, the null hypothesis is that the average mean, or the mean of the population of all of my solves, which sounds again a little ridiculous, is 25. The claim is that the mean is actually less than 25. So notice this is a left tail test. Nice. So we're expected to get a negative number for our test statistic, and let's see what happens. So now step 2 is to find our test statistic, which is T naught, and it's going to be, if you don't remember, it's x bar minus mu naught over S over radical n. So with these values, it's 2.45 minus mu naught, which is 25. That'll for sure give us a negative value over 3.27 divided by the square root of 6, because the sample size is of course 6 here. So now let me calculate this on my calculator off screen. We'll see what we get, but now before we get there, remember that step 3 is finding the p-value. Now the p-value is going to be the area of this tail region. Now it's a left tail, so we're going to go from negative infinity. It's going to be a t value, or t area, so it's under the t curve. So it's going to be from negative infinity to our t value. And our degrees of freedom are 6 minus 1, which are 5. Okay, it's not very hopeful because this is pretty close to 25, but we'll have to see. So again, the t curve looks something like this. Our t statistic is going to be somewhere on the left over here. And we want to find our p value, which is the area of this. Basically, we want to see if the area is less than our level of significance, which again is 0.05, because the confidence level is 0.95. So maybe that's something I should note here. This implies that alpha is equal to 0.05, which I think is fairly obvious. So now let's get cracking into this. So let me kind of give some space here, and let's see what we get. All right, so where we left off was we found p. It was about 0.36. That's not less than our level of significance, 0.05. So we do not reject h naught, and remember this is really step 4 of the process. And this implies that there is insufficient evidence at the alpha equals 0.05 level of significance, or you could say we're 95% confident that this is the case, that there's not insufficient evidence or insufficient evidence to support the claim that his average, my average, is lower than 25 seconds. So I suspect that this guy is kind of a problem there. So maybe I should have been a little, quicker there, or maybe redone it to make it seem like, I can actually solve faster on average. But yeah, I'm a little rusty, so that's okay. But anyways, we saw we saw two examples of do not reject, we saw two examples of reject. So I think I've done my job as far as showing you what we need to see. Now again, this hypothesis testing video it was only on testing hypothesis for the mean. Now there could be hypothesis testing for different parameters like we talked about. There's proportion, there is standard deviation, variance, and those require different test statistics. They require different distributions. Now for proportions, they actually require the normal z-curve, so that's fine. But for testing something like variance or standard deviation, that involves something called chi-squared. Now if you look in your calculator, chi-squared is actually below the t distribution. And yeah, I don't think we're gonna have time to talk about that, obviously, especially not in this video. But I just wanted to throw that out there, that hypothesis testing, it can go on, and similar for confidence intervals as well. That conversation can be longer than the ones we've had here, but this and the confidence interval one was specifically for the mean. And I showed you two different cases where either sigma is known or it is not known. So with that being said, I really hope you enjoyed this video and the explanation on hypothesis testing. Thanks for watching.